Operational amplifiers are an essential part of electronics, so much so that despite the decades, many designs made in previous decades are still in use in one form or another. Clearly, using BGT technology OPAMPs is not precisely the best option today, so we are going to analyze an OPAMP with better performance than general-purpose OPAMPs like the LM358 or the LM741. We will review a superior architecture, the JFET architecture. For this comparison, we will use the TL084 OPAMP. First, we have the internal structure of this OPAMP. We can see that its internal structure is practically the same as that of a conventional OPAMP, except that it uses JFET transistors at the input instead of bipolar transistors. Similarly, the current reference also uses a JFET transistor. What does a configuration like this offer us versus a completely BGT architecture? We have several advantages. The most notable is a much lower bias current. The second advantage is a faster slew rate, and the third is a higher operating frequency. Let's look at TL084 datasheet to see the characteristics. First, we have the recommended operating conditions. For the supply voltage, we have a minimum of 5 volts per rail and a maximum of 15 volts per rail. If powered with a single rail, we have a recommended maximum amplitude of 30 volts. For the operating temperature, it depends on the model. We have temperatures ranging from 70 degrees to 125 degrees. Next, we have the electrical characteristics. First, we have the input offset, which has a maximum value of 20 millivolts. Then we have the offset affected by temperature coefficient with a value of 18 microvolts per degree Celsius. Next, we have the input bias currents. In this case, we have a maximum range of 2 nanoamps, which is a very low value possible due to the JFET inputs. Now we have the bandwidth, obviously with unity gain, being 3 MHz. It is important to remember that the greater the implemented gain, the lower the bandwidth. Next, we have the consumption current per amplifier, with a nominal value of 1.4 milliamps and an output short circuit current value of 26 milliamps. And finally, we have the crosstalk attenuation value, which is 120 decibels. Next, we have the switching values, indicated a minimum slew rate of 8 volts per microsecond and a typical value of 13 volts per microsecond. A rise time value of 0.05 microseconds and an overshoot factor of 20%. Well, now that we have seen the datasheet values, it is time to verify them in the lab. Do you have a project that needs to be finished? Do you have an idea for a product and you want to take it to the next level? We are your best choice. In Prisma Network, we have the best team to do so. We offer services on hardware design and software design. From PCB development, firmware development, app development, and desktop development. We offer competitive prices and an excellent service. Contact us to get a quote. All of the info available at the video description. So here we have our offset input and output difference. We're going to measure both values with our multimeter. Let's see what happens. We can see that basically we have a 1 millivolt of difference, around 1 point something millivolts of difference. So we are seeing some good enough precision for many cases, which is a good thing compared to other models of OPAMPs. Now we're going to do measurements with the temperature offset. We're going to see the difference between the input and the output. We can see that we have a 3 millivolt difference around this value. We don't have much difference. Now we are going to test the bandwidth of the OPAMP. we're going to test it with a sine wave. We can see that we are already at 1 MHz and there is some distortion. We can see that we already have distortion on the signal, which is turning into a triangle wave, and we are seeing attenuation as well. We are at 3 MHz, which is above the established unity gain bandwidth that we have with the OPAMP. Let's go back at a lower frequency, and we can see that around 1 MHz we have the optimal performance. And now let's test the consumption current of the OPAMP without a load, of course, and it is around 1 milliamp. So we can see that the OPAMP is not really consuming that much energy, although if we had a battery operated circuit, maybe this will be a very high value. So even though it's not high precisely, it will be very high for battery operated circuits. So we will have to look at another solution. And now let's test the short circuit protection. We can see that we are below the maximum value, which was around 26 milliamps, and we have the output of 5 volts. When we increase the value, we can see that the output is going down because it has to protect the current that is going in the output. And how do we protect it? By lowering the voltage. It's simple Ohm's law. So the higher the current goes, the less voltage we're going to have in the output. And this is basically how this protection happens in any device, not only in OPAMPs. We have 2.9 volts at 37 milliamps from 5 volts that we have previously. Here we're going to test the maximum power supply voltage of the OPAMP, which was around 30 volts. We're going to go above and see how it behaves. Going above 40 volts and the OPAMP is going to start to behave improperly, and we may also damage it irreversibly. We go back, and it seems that we have already damaged the OPAMP. And at this last test, we're going to measure the overshoot factor and the slew rate. We can see that we are measuring the slew rate, or the rising and falling time of this square wave, to obtain the value in microseconds. And we have 530 nanoseconds of this rising edge, so we are getting very good values in this case. What difference does this OPAMP have compared to another that is completely bipolar architecture? Let's compare it to the LM324. In most values we have very similar quantities, so there are not very notable differences. Where the changes are more noticeable are in these 3 parameters. First, we have the input bias current value, which is between 45 to 100 nanoamps for the LM324, more than 30 times higher than the TL084. Second, we have the slew rate. In the LM324, we have a slew rate of less than 4 volts per microsecond, in contrast to the TL084 value, which is 13 volts per microsecond. Finally, we have the bandwidth, which is 1 MHz in the LM324 versus 3 MHz in the TL084. So what is our conclusion? Amplifiers with FET transistors implementation, whether partial or fully, definitely offer many interesting benefits for performance.